Hi everyone. In the last video we looked at the conservation of momentum. This time we're going to be looking at situations where things like the velocities might change or the direction that the objects are traveling in might change. So we're looking at momentum transfer. So we're kind of talking about a change in the kinetic energy. And we call this change in momentum impulse. And the formula used to calculate impulse is equal to the change in momentum, and change in momentum is equal to the mass multiplied by the final velocity minus the mass multiplied by the initial velocity. So this can be seen in this formula here. You can also refer to your notes, which I've put on Compass for you. Alright, so let's have a quick go of an example. We've got a student and they're riding their bike. The student and the bike weigh 80 kilograms. And they are riding at 8.2 meters per second to the east, and they're about to arrive at the school rack at school, where they're going to come to a complete stop. Okay, so we've got our mass. We know the bike and rider are 80 kilograms. They initially travel at 8.2 meters per second to the east. We know their final velocity is going to be 0 because they're coming to rest. So we use our formula. Impulse is equal to mv minus mu. So we have 80 times 0 minus 80 times 8.2. So the impulse, or the change in momentum, is 656 kilograms per meter per second to the west. So it's in the opposite direction that the person was originally traveling. So that is the impulse, or the change in momentum. Alright, it's really as simple as someone traveling in one dimension, and we often have to resolve things using geometry. And there's a couple of tricks here that you need to be really careful of. Now, the example that we're going to have a look at is a 65 kilogram mass, and it's initially traveling at 3.5 meters per second to the west. It's then going to change direction to the north, and it's going to travel at 2.0 meters per second. And we need to calculate the change in momentum. But before we can get to the change in momentum, we've got to resolve the vectors for direction. So we need to find out what has happened, what's the change in velocity, and what's the change in direction. Okay, so the first thing we start with is the fact that we were traveling 3.5 meters per second to the west, and usually we would represent that by the negative. In the equation though, we need to take the negative of the initial velocity. So you know, when we have two negatives, that's going to become a positive, or 3.5 meters per second to the east in the positive direction. So when I draw my diagram, I've got my north going up, and then I've got my east. We're traveling to the east, so that I could resolve the double negative. Which means, therefore, I've got the hypotenuse running from this point through to there. And this is what we're going to talk about as the change in velocity. Now, we're going to apply Pythagoras to this question. So the change in velocity squared is going to be the other sides, so 2.0 squared and 3.5 squared. So we need to take the square root of 16.25. So the change in velocity is going to be 4.03 meters per second. Okay, so that tells us what the change in velocity is, but we actually need to find the direction for that change in velocity. So we need to work out what theta is for this triangle. Therefore, of course, we're going to go to our SOHCAHTOA to do that. Alright, so because I've got the opposite and the adjacent, I'm going to apply tan. So tan theta, I've got 3.5 over 2. So that gives me theta of 60.3 degrees. So I know that the change in velocity is 4.03 meters per second, and the change was north 60.3 degrees east. So if you have a think about it, we're going that way, so we're talking about the northeast quadrant. Alright, so now I've got my change in velocity and I also know the direction. Because this is a vector, we must have that direction. I can finally work out the change in momentum, which is what the question actually asked. Okay, so I know that change in momentum is equal to mass times the final velocity minus mass times the initial, or it equals mass times the change in velocity. Okay, so that's another way of writing mass times change in velocity. And you've already worked out what the change in velocity was. We did it up here. It was 4.03. So I've got a mass of 65 multiplied by 4.03. So that's going to give me 262 kilometers per meter per second. And if we put that all together, our change in momentum therefore will be 262 kilograms per meter per second, north 60.3 degrees to the east, which gives us our final answer. So we've got the change in velocity plus we've indicated the direction that that change in velocity occurred. So one of the tricky things to remember is to remember this negative initial velocity, because we were talking about traveling to the west, but the double negative meant we had to change that to traveling to the east. And that's where a lot of students get stuck when solving a problem like this. So watch out for that double negative situation. All right, I'll see you in class. Bye.